Very good afternoon to one and all. So today we are going to see about formation of fibers by using singular transformation. Formation of fibers by using singular transformation. Okay. So in this, first for that, you need to know about what is graph theory. Okay, so fibers can be found by another method is known as singular transformation. Okay, singular transformation. So we are using the graph theory to determine the bus admittance matrix. So previously, what we did, we just found out the bus admittance matrix directly. So now we are going to find out the fibers matrix by using the graph theory method. That is nothing but singular transformation method. Singular transformation method, or by using graph theory. Okay. So say for example, what is a network? Network is an interconnection of elements in the various branches and different nodes. Interconnection of elements. Say for example, in this figure, one network is shown. Okay. Network is shown. So there are various elements are there. Various elements are there in various branches and in the different nodes. Say, for example, in this, in this figure, there are four nodes are there. 1, 2, 3, and 4. Four nodes are there. And there are interconnection of elements also there. Okay, interconnection of various elements in various branch at different nodes. So that is called the network. So you need to know what is a network. Next, what is a graph? A graph is a representation of network obtained by replacing every element of a network by a line segment. So whatever there in the network, what we are doing is we are just replacing every element by a simple line segment and every junction by a node. Okay, so every junction by a node, each and every junction we are making this node, and every element, okay, so by a line segment, okay, and line segment. So that is a graph. A graph corresponding to the network issue. So here, the same network, what we are doing is we are converting into the graph. Okay, so here this is a network. So we are converting into the graph. So what we are doing is we are converting this element into a straight line. So here also element is the straight line. Here also element, here resistance element is the straight line. Here, okay, here inductance element is the straight line. Here inductance element is the straight line. Here E inductant elements is the straight line. So sorry, the capacitive element is the straight line. So here resistance element is the some line. Straight line or some line. So what we are doing is you can also draw a line, okay, or otherwise like a curved line. Okay, so for a better understanding, you can draw any kind of line. Okay, but if you draw line like this, okay, it will become some again a node. So that's why we are going like this. Okay, so we are connecting like this off circular, like parabola, like that. We are off circular like that we are connecting. Okay, so if you connect by this triangular, again this here one node will come. Okay, again many confusions will come. So to avoid that, like that we are doing. So this is being converted into like this. Okay, so like this, so node also we are marking. So that is nothing but a graph. What is oriented graph? Oriented graph is nothing but if every branch of a graph has a direction, if every branch of a graph has direction, then the graph is called directed graph or oriented graph. Okay, so in that every branch of a graph, this is a graph. In every branch have some direction. Say for example, 1 to 2. Here A is one direction. Here D is one direction. C is one direction. B is one direction, E is one direction, F is one direction. Okay, so that is called oriented graph or otherwise directed graph. Okay, so that is shown in the figure, oriented graph. Okay, so you need to understand the difference between the network graph and oriented graph so that you can easily okay, so see any network if you given in the problem, you can easily convert that into graph and as well as the oriented graph based on the network. Understood? Next step. by a branch or edge. Okay, branch. A branch is represented by a line segment in a graph of a network as shown. So graph is represented by line segment. Okay, line segment in the graph of a network shown in this network. Already we have seen in the graph itself. A branch is represented by a line segment. So what we had done is, so one branch we converted that element to line segment. Okay, or edge. We can call it as edge. Okay, sometimes edge. So mostly we'll call it as branch only. In some other notations, they will be called as edge. Okay, next node or bus or vertices. So what is meant by a node? A node is a terminal of a branch which is represented by a point. Okay, so as we see here now. Okay, so these are all each and every nodes. This is one node, this is second node, the third node, and fourth node. So you need to put one dot here. Okay, some dot here. So so you can easily identify that is a node. Okay, a node is a terminal of a branch which is represented by a point like this. As I said, you need to put a point so that easily you can identify that as a node. So what is meant by a loop? Loop or a closed path. If starting node and ending node is same for a path, okay, then it is called a closed path or a loop. Okay, so that all already know. There are two nodes are there. So here, what is the starting and ending node is same for a path. Starting and ending node. See, it is starting like this and ending here. Okay, so starting and ending node is same for a path, then it is called a closed path or a loop. That we already know. So what is meant by a tree? A tree is a subgraph of a network which consists of all the nodes as in the graph, but has no closed path. No closed path. Okay, so this is called a tree. Okay, so no closed path. A tree is a subgraph. Okay, subgraph. So with the graph, what we are doing is subgraph of a network which consists of all the nodes. So it consists of all the nodes. So from the previous graph, so it consists of all the nodes, but has no closed path. It should not have any closed path. So here also no closed path. Here also no closed path. Okay, so like this. So here, like this, here also no closed path, here also no closed path. Okay, so that is called a tree or twig, TWIG, twig. Okay, what are the properties of tree? Okay, so what are the properties of tree in the sense? Number of nodes in a graph is equal to number of nodes in a tree of that graph. Okay, what are all the nodes in the graph? That is equal to number of nodes in the tree of that particular graph. Okay, all the nodes must be connected by elements called tree branches. All the nodes must be connected by elements called tree branches. And the next, tree branches must not form any loop or closed path in the subgraph. Okay, all the nodes must be connected by elements called tree branches. Next, tree branches but must not form any loop or closed path in the subgraph. Okay, in the subgraph, tree branches should not form any closed path. Okay, next, every connected graph has at least one tree. Okay, every connected graph has at least one tree. Next, rank of tree is equal to rank of graph. Okay, rank of tree is equal to rank of graph. This is another one properties of a tree. Okay, so next, number of trees equal to number of nodes minus one. That is n minus one. Okay, so how many number of trees means number of nodes minus one. So that is the say for example here 4 nodes are there. Okay, how many number of trees are there? 4 minus 1. So 3. Okay, so three branches are there. Number of branches equal to node minus 1. That is n minus 1. So here how many nodes are there? 4 nodes are there. 4 minus 1 is 3. So number of 3 branches are 3. Okay, so this you need to understand, remember and understand. Okay, so for solving the problems. Next, what is meant by a link or cord? Okay, removal of branches of a tree is called links. Removal of the branches of the tree is called links. The branches of core tree is called link or core. Okay, so like this, removal of branches. So like the dotted line they mentioned, no, removal of branches of a tree is called links. The branches of core tree is called link or core. The different links of graph is shown in the figure. So these are the different links that is shown in the figure. Okay, next, what is core tree? The set of all links of given tree is called core tree of the graph. The set of all links of given tree is called core tree of the graph. Next, you need to understand what is cut-shed schedule. Okay, cut-shed schedule. Then for incidence matrix, formation of incidence matrix, that will be useful. Okay, so that's why we are seeing some basics now. Then we were into the thing. Okay, so that's why we are in the basics. Okay, so next step. What is cut-shed schedule? What is cut-shed schedule? Cut-shed schedule is nothing but an alternative method of finding out branch voltage is called cut-shed schedule. Alternative method of finding out branch voltage. Okay. So that is the another alternative method of finding the branch voltage is known as cut-shed schedule. So what is cut-shed? Cut-shed, it consists of one and only one branch of the network tree together with any links which must be cut to divide the network into two parts. What is the cut-shed? It consists of one and only one branch of network tree together with the links. Okay, together with the links must be divided, which must be cut to divide network into two parts. Okay, so example we'll see. Example we'll see. Okay, say for example, this is the network. This is the network. Okay, so this is the graph. Some one graph. Okay, so that is example. So first step. First you need to draw the tree. First you need to draw the tree. This is the graph. Okay, this is the graph. So for this graph, what we need to do is we need to draw the tree. What is tree? So we need to avoid the closed loop. Okay, we need to avoid the closed loop. That is called a tree. So we have already seen what is tree. That is tree. Yeah. Tree is a subgraph of the network which consists of all the nodes and as in the graph, but has no closed path. We should not make the graph to closed path. So whatever the graph is given, in the problem, so that we are not making it to closed path. So that is we are opening here. So the tree is nothing but it will not form any closed path. Okay, so we are opening this. Okay, next step. Step 2. Okay, so this is the steps for cut-shed schedule. I hope you are all noting down it correctly. So cut-shed schedule. So what is the first step? You need to draw the tree from the graph. That is the first step. What is the second step? Give the naming for tree branches first, then to the link. Tree branches first you need to give the naming for tree branches and then to the link. Assume tree branch direction away from the cut set. Okay, and assume link direction as clockwise. So tree branch direction away from the cut set and assume the link direction as clockwise. Okay, so like this. So what we need to do is for the step number 3 is form the bus incidence matrix. Form the bus incidence matrix. Okay, so in that, write the matrix equation for each cut-set schedule using the Kirchhoff's current law. So first assumption is current away from the, this is a very important thing you need to note down. Current away from the cut-set or node is taken as positive and the current towards the cut-set is taking, cut-set is negative. Okay, current away from the cut-set or node has to be taken as positive current towards the cut set. Okay, current towards the cut set, you need to take it as negative. Okay, so that is what given here. Okay, so this is the tree, that is the dotted line. So that we are not making the tree to the in the closed loop path. So we are making the dotted line. So now what we are doing is we are making the we are naming the first three branches first, then to the link. Three branches we are naming. Assume tree branch um, direction away from the cut set, and assume the link direction in the clockwise. Link direction in the clockwise. So link direction outside link, it should be in the clockwise direction. See, like this. So like this arrow. Like this arrow mark, link direction you need to give outside. Okay. And what else? Three branch direction. Assume the three branch away from the cut set. That's it. So this, say for example, you take four nodes, 1, 2, 3, and 4. Okay, this is the cut set 1, cut set 2, cut set 3, and cut set 4. So whatever the cut set, we need to mark this away from that nodes, away from the nodes. Okay, so that is what given here. Three branch direction away from the cut set. So okay, say for example, you are taking like this. Okay, so this is A. Okay, from here this is B. From here this is C, and from 4 node this is D. Okay, so like this, and this outer part, you need to kind of what do you call, direct. You need to give the direction in the clockwise direction. Clockwise direction. Okay, like E, F, because as being this is the first node for 1, 2, 3, and 4. So we are starting from here. Okay, you may get the doubt. So why here E? Why here F? Why here G? Why here H? So first you need to mark this A. Okay, from the node number 1 A, node number 2 B, away from the node. Okay, node number 3 C. Okay, node number 4 D. And from the reference to the node number 1 in the clockwise direction. So here we are giving E. Here we are giving F. Again, here we are giving G. Here we are giving H. Okay. So this is the thing. Okay. So this is the thing. So this is the loop number 1, 2, 3, and 4. Okay. So the loop number 1, loop number 2, loop number 3, and loop number 4. Okay. So let IBA, IBB, IBC, IBD, IBE, then IBF, IBG, IBH be the branch currents for the elements. Branch currents for the elements A, B, C, D, E, F, G, H. Okay. So let IBA, IBB, IBC, IBD, all the combinations. IBE, say for example, IBA. Okay, IBA. Okay. So where is the, yeah, IBA, IBB, self, IBC. Okay, IBC. Next IBD, IBD. Next IBE, IBE. Next IBF, IBF. Next IBG, IBG. Next IBH. All the combination be the branch currents for the elements A, B, C, D, E, F, G, H. Okay, so this we are assuming, or we are assuming, yeah, exactly we are assuming. So now we are forming the cut set 1, 2, 3, and 4. Okay, cut set 1, cut set 2, cut set 3, and 4. So cut set 1. So here these are the A, B, C, D, E, F, G, H. Okay, what is A, B, C, D, E, F, G, H are the branch currents. Okay, branch currents. So here first cut set 1. Cut set 1. So this is the cut set. This like this, you that cut set like that, you like that we draw now. So this is the cut set 1. Okay. So here from the cut set 1, so whichever the direction it is, say for example, going out, we need to take as 1. Okay, going out. Going out, we need to, whichever the direction coming inside to the, cut set one, that is node number one, that we need to take it as -1. H is coming inside. So we are taking this -1. So what else? E is going outside. So we are taking this 1. Okay, just all others are 0. No need of bother about all the other elements. Okay, sorry, not elements, direction current. So just a 0. Next, all elements are 0. Okay, so next, similarly, cut set 2. Cut set 2, what? So cut set 2, we now we'll tell. So what are all the things going outside? So B and F going outside, E is coming inside. So for E is -1. B and F is 1 because going outside. Okay, let's see here. So B and F 1. So E is -1 because coming towards the cut set 2. So it is -1. Rest all are 0. Next, similarly, cut set 3. Cut set 3 is what? So it is going outside. C is going outside. Okay, C is going outside. C and G is going outside. F is coming inside. So outside means -1. Inside means 1. Sorry, inside means -1. Outside means, so outside of this thing is 1. Okay, so here you see inside it is coming. Okay, F is coming inside. So that is -1. Rest are all. So rest C and G. C and G is going outside. That is 1. Going outside means 1. Coming inside means -1. Rest are all 0. Similarly for cut set 4. Okay, so what are the elements? Cut set 4. D and H is going outside. Going outside means D and H. Okay, D and H is going outside means 1. Coming inside. G is coming inside. So -1. Rest are all C. Okay, so into that branch current. So first branch current, yeah, the say similar way. IB, IBA, IBB, IBC, IBD, IBE, IBF, IBG. So that is equal to 0. Okay, so that is nothing but here, that is nothing but the whole thing A. So here they divided like AB into AL, I think so. Okay, so AB into AL. Okay, so as a whole, this is like A. Okay, so where A is nothing but bus incidence matrix. So IB is nothing but branch current. IB is nothing but this branch current. Okay, branch current matrix. Branch current in the matrix form. So okay. So next, number of cut sets equal to number of 3 branches. Number of cut sets. So how many cut sets? 4 cut sets. So how many number of 3 branches? 4. So that is equal to 4. Next, express the branch voltage in terms of branch, 3 branch voltages. Express the branch voltages in terms of 3 branch voltages. Let VBX be the branch voltages. VBX be the branch voltages. Okay, so let VX be the 3 branch voltages. 3 branch voltages. So branch voltages VBA is equal to BA. Okay, so that is here. Yeah. BBA. BBA is equal to BA. BBB is equal to BB. Okay. BC. Okay. BBC is equal to BC. BBD. Okay. BBD. So we can see here BBA. Okay. Voltage in BBA is nothing but BA. Okay, so now framing the loop equation 1. Loop equation 1. Loop, what is loop equation? So this is the loop 1. This is the loop 1, loop 2, loop 3, and loop 4. Okay, so according to that, we need to frame the loop equation. So what is loop equation? First loop equation. So first loop equation here it is VB minus VA plus VBC is equal to 0. Okay, VB. So if you take it in the this clockwise direction like this, VB minus VA, why? So it is coming in opposite, that is the arrow mark direction. If you take this as arrow mark, okay. So if you take this as arrow mark like this, we take the arrow mark like this. Okay, so this is VB minus VA. VB minus VA. Okay, so VB minus VA plus VBC is equal to 0. Okay, plus this total voltage between the this particular loop. Okay, so that is nothing but VBC. Okay. So like this, you need to formulate the loop equation 1 plus VBC is equal to 0. So here printing mistake, VBC is equal to VA minus VB. So here loop equation 2. Okay, similarly loop equation 2. What is loop equation 2? So here if you frame the loop like this, okay, so loop like this means BC minus VB plus VBC. Okay, so like this here. Sorry, BBF, where it is BBF, not BBC. So here F is there, na BBF, BF. Okay, so here BBF plus BBF, okay, plus VC minus VB, minus VB, okay, minus VB, because it is coming in the opposite direction. VB is coming in the opposite direction. Okay, if you take the loop like this, so BC minus VB plus VBF is equal to 0. So VBF is equal to, so from the loop equation to VBF is equal to VB minus VC. Next, similarly, loop equation 3. Okay, so what is loop equation 3? So we need to go to here, loop equation 3. What is loop equation 3? So it is like this, VB minus VC, okay, plus VG C. Okay, VBG. Okay, VBG. Okay, VD minus VC plus VBG. Next, what is the loop number 4? Here, VH. Sorry, this is loop number. It like this it is coming. So VA minus VD is equal to VH. VA minus VDC plus VBH is equal to 0. So VBH is equal to VD minus VA. So this is the loop number. So similarly in matrix format. So in matrix format is nothing but VBX is equal to A transpose into VX. VBX equal to A transpose into VX. So VBX, okay, similarly, we need to, that current combination we wrote, no? Similarly, we need to write voltage. VBA, VBB, VBC, VBD. So VBE, VBF, VBG, VBH. Okay. So the H, so this is the VBX. Okay. So next is nothing but A transpose. A transpose what? A, we already, this is the A matrix. Okay, as a whole, I said no. This is the A matrix, bus incidence matrix. So this we need to transpose. So A transpose means, so this will come this side. Okay, row to column. Okay, so we need to transpose. So this 1 0 0 0 1 0 0 minus 1, like that it will come. So let's see 1 0 0 0 1 0 0 minus 1, like that. So it is what we are doing is simply we are transposing into VX. So VX is nothing but, so only branches, that is VA, VB and VC. Okay, so that is branches in the row. So these are the elements. Okay, so these are the whole elements. Okay, so next step. What is A transpose? That you know, A transpose nothing but what are all the things coming in that particular matrix, that is you have to transfer. What is BX? BX is nothing but branch voltage matrix. Okay, BX nothing but branch voltage matrix. A is nothing but incidence matrix. A is nothing but incidence matrix, but here we are transpose incidence matrix from the previous thing. What is Vx? Vs nothing but tree branch matrix. Tree branch matrix. So this matrix is rectangular and therefore singular. So if elements A, I, K can be found as per the rules. That is A, I, K is equal to 1. If ith node is incident to and oriented away from the kth node, then Aik is equal to -1. If ith node is incident to and oriented towards the kth node, if Aik is equal to 0, if ith node is not incident to the kth node. Okay, so this is how we need to calculate the incidence matrix. Okay, incidence matrix is A. Okay, and okay, so from this, okay, so this is the VBH or branch voltage matrix equal to A transpose into tree branch matrix. So this is the important formulation. This you need to note it down clearly. VBH is equal to, that is branch voltage matrix equal to A transpose into tree branch matrix, that is VX. So this is the important formulation that we are going to use in our for solving the form problem solves. Next, coming to the primitive impedance matrix. What is primitive impedance matrix? That is Z primitive matrix. What is primitive network? A network element may contain active and passive components. Okay, a network element may contain active and passive components. Okay, say for example, in the impedance form, it will consist of both active and passive components. Okay, next in the admittance form, how, say for example, here impedance form, it is given like this. Okay, so voltage source given and ZB is given. In admittance form, it will be given like this, YB, like that it will be given. So YB is equal to 1 divided by ZB. This already we know. Okay, from the previous classes already we know. Okay, a set of unconnected elements is defined as primitive network. A set of unconnected elements is defined as a primitive network. If no mutual coupling between the elements, the diagonals are impedance or admittance. If there is no mutual coupling between the elements. Okay, so the diagonals are impedance or admittance. Okay, so diagonal elements alone, the impedance are admittance if there is no mutual coupling. Matrix which contain information about transmission line impedance is called primitive impedance matrix. A matrix, say for example, what is Z primitive matrix? Is nothing but a matrix which contains information about the transmission line, that is impedance. Okay, transmission line, that is impedance value, is called primitive impedance matrix. Say for example, this is the example is given, Z primitive matrix equal to. Okay, so like that. So these are the number of elements or branches. Okay, A, B, C, D, E, F, G, H. Okay, as we see in the previous graph, we have seen, no? See, these are the number of elements, say for example. So what is this? A matrix which contains information about the impedance in the transmission line, that is particular transmission line. Say for example, between the elements A and E, ZE. Okay, so between the B and B elements, ZB. C and C, ZC, like that. Similarly, so all other terms are 0. The diagonal elements are self-impedance of the elements. Self-impedance of the elements. So off-diagonal elements, no. So 0. Off-diagonal elements, 0. Okay. So this is called a primitive impedance matrix. Primitive. So say for example, if it is a, what is Y primitive? Same thing. So if the matrix which contains the admittance matrix, then it's called primitive admittance matrix. That's all. Okay, it contains all the values of their admittance of that particular transmission line. Okay, so this is one simple example they have given. Okay, so you just take, so any size you can take, not only A, B, C, D up to H, any size, because we have taken in that example, in the previous example, up to H, so that we have taken as H. So it is up to N. N means up to Z, or up to how many combinations it is there, how many branches, how many elements it is there. that many elements we need to add. It is not only up to A to Z. So maybe N, okay, 1 to N. So it might be keeps on going as your elements and branches are increasing. So if you draw this for your practical case, then it will be this matrix will be like a n cross n matrix. Okay, so no limits. How many branches? Say for example, some 1 lakh branches also there. 1 lakh branches we need to add. Okay, if you take the practical case. Okay, next, if a mutual impedance ZM is given between the branches, say for example B and C, mutual impedance, then the direction of the current is same. Then the direction of ZM is positive. If the direction of current is same, say for example, the direction of current is same, then the mutual impedance is positive. Say for example, how this mutual impedance comes, say here A, B, C, D, E, F, G up to H. Okay, so here B and C. Between the B and C, what is ZM? Similarly, between C and B, again, one mutual impedance is there. So that's why here we are adding the ZM here. That is mutual impedance, the same primitive admittance matrix. Okay. So if the current, say for example, if the current is in opposite direction like this, then the ZM is negative. So here you have to add mark negative. Okay. If the current is in opposite direction, that you need to remember. So one of the key points you need to remember. So what is primitive admittance matrix? Matrix which contains information about the transmission line, that is admittance, is called primitive admittance. Primitive admittance matrix is the inverse of primitive impedance matrix. Okay, so Y primitive is equal to Z primitive inverse, that you already know. Okay, so Y is equal to 1 by Z or Z inverse. Okay, so that. So what is bus admittance matrix? We know like A into IB is equal to 0. From the previous formulation, A into IB is equal to 0. So where from here, A into IB. Yeah, somewhere around here we have seen A into IB. I think from the previous class, we need to go to previous, here, not previous class, here. A into IB is equal to 0. A is nothing but incident matrix. So this matrix we are taking over here. A into IB is equal to 0. Next, BB is equal to A transpose into BX. That is branch. So here we formulated, no, I said it is very, very important, like VBX, branch voltage matrix equal to A transpose into 3 branch matrix, BX. Okay, so that is here. That is VB is equal to A transpose into BX. Okay, so take this as some equation number. So say for example, in the figure, so this is some examples being given. So having one current source IG here in direction like this, and one voltage source here, direction here like this. Next to YB. Okay, so admittance is given YB. So voltage between this is VB, and here also IB. Current here we are injecting as IB. So here we are writing the KCL. Okay. We are writing using Kirchhoff's current law. Okay, Kirchhoff's current law. So IB is equal to minus IG, because if you take the reference like this, so this is in opposite, minus IG plus YB into BB minus BG. Okay, so BB minus BG. So this you take some equation number. So similarly, what you need to do is substitute IB from equation number, say for example, this is the equation number 3.26. Substitute IB in the substitute IB from the equation in this equation. Okay, in this equation, if you substitute this 2 here, so A into minus IG into YB into BB minus VG is equal to 0. So that we need to substitute. Okay. So next step, we need to multiply this, because A into, so A matrix, what is A? Incidence matrix. So this we need to multiply. If you multiply minus A into IG plus A into YB into BB. So minus here, minus is coming. So A into YB, so equal to 0. So again, what we are doing is substitute VB in the VB from above equation, that is equation 3.25 in the above equation. Okay, so what is VB here? So VB is nothing but A transpose into Vx that already we formulated from the previous equation. So here we are simply substituting for VB here. Okay, so if you substitute and again rearranging this, okay, multiplying all these terms and taking the common terms outside. Okay, so outside you'll get the equation like this: A into YB into A transpose into Vx, the whole bracket into Vx, and also equal to A into YB into VG plus A into IG. So this we have to take as Y bus. So Y bus, but bus admittance matrix equal to A into YB into A transpose. So this is the very, very important formulation you need to remember. Okay, bus admittance matrix equal to A into YB into A transpose. Okay, so into Vx is equal to I bus. Okay, so that is equal to I bus. So this is the very, very important formulation, that is Y bus matrix, that is bus admittance matrix equal to A into primitive matrix, okay, into A transpose, where Vx is nothing but a tree branch voltage matrix. Okay, so V is nothing but tree branch voltage matrix. So so this is a very, very important formulation where Y bus is equal to A into Y primitive into A transpose. Because we are, say for example, here we are going to use this in the problem for solving this formation of bus admittance matrix by using the singular transformation method. Okay, so this is how the singular transformation method. This is how we need to calculate. Okay, so Y bus equal to A into Y primitive into A transpose.